Good afternoon, everyone. So my name is James Forbes. I'm a professor in the Department of Mechanical Engineering at McGill University. I'm also a member of the Center for Intelligent Machines at Gerard. And I'm very pleased to introduce Stephen Dahdah today, who's a PhD student in mechanical engineering at McGill University. He's a member of my group, the DECAR Systems Group. He completed his undergraduate degree, his B.Eng in Honors Electrical Engineering at McGill University in 2019. He did a minor in software engineering. He started his M.Eng studies in my group in 2019 and fast-tracked in 2020 to the PhD program. In addition to being a great resource in the lab with all things Python and all things electrical engineering related, he also does research on data-driven modeling and control techniques, in particular motivated by a particular industrial robot. Specifically, he's been working with Macademic that makes a very small, compact industrial robot. And his PhD work is also funded through MyTax, where in collaboration with Macademic, Stephen is looking at enhancing their existing control techniques with some more data-driven control techniques, as well as some optimal and robust control techniques. So I'm very pleased to invite Stephen to give his presentation. And yeah, take it away, Stephen.
Thanks. Thanks for the great introduction. I'm flattered. I'm going to share my screen now. And then, where are we? Participants can now see your screen. Okay, cool. So thanks everyone for having me. It's a really great opportunity to be able to speak for you all. Today, I'm going to talk about data-driven modeling and control with the Koopman operator. Yeah.
We actually did see your desktop.
You just see my desktop?
Not your slides.
Oh my God. Okay. Let's see. You should be able to see it now then.
Yep.
Okay. My bad. Shared the wrong desktop. I'm getting old. Okay. So yeah, data-driven control and where are we? Yeah, data-driven modeling and control with the Koopman operator. So there's a lot of ways you could kind of arrive at the Koopman operator or reasons you would be interested in the Koopman operator. But the angle I'm going to take here is industrial robot control and specifically optimal control. So this is Macademic's Mecha 500 robot arm. And a lot of the tasks that it has to do are like pick and place operations, assembly. There's also inspection, testing, dispensing. This robot can't weld or anything. But in all of those tasks, we care about a couple of performance metrics. We care about the repeatability for tasks where you want to go from one point to one point without really caring how you get there. Or you might care about the path tracking error, or the path tracking accuracy for tasks where you care about the whole trajectory, going along a weld, for example. So for all of these tasks, as I'm sure you know, in addition to like a solid mechanical design and all that, you need feedback control to do all of this. So one way to do feedback control that's a very popular tool in robotics is optimal control. So in this workflow, you start with often a nonlinear model that you've derived from first principles like Newton-Euler or Lagrangian mechanics. And to actually use these tools, you need to linearize the model. So you choose an equilibrium point and you find a linear model that's valid near that equilibrium point. This is a local approximation. And then once you have that linear model, using your A and B matrices, you can synthesize a controller by posing an optimization problem. So you would say your criteria would be, I want very low tracking error, and you want to also not overuse your control inputs. So by balancing the control effort and the path tracking error, you end up with a controller that's in this case optimal for the linearized model, but not necessarily optimal for that nonlinear model. So this approach has some advantages and disadvantages like everything, some trade-offs. The nice thing is that it leverages our knowledge of the dynamics. In a lot of cases, we do know a lot about how the robot behaves. So we want to use that information instead of just randomly like tuning PID gains. It's also really systematic, it's easy to tune, and it helps us evaluate trade-offs. So if you're hand tuning a PID, you might end up accidentally creating an unstable controller or making a strictly worse controller. But in this case, with optimal control, you're kind of staying at the interesting trade-offs between control effort and error. And of course, since this is a super old, well-studied field, there's lots of extensions to handle nonlinearities, either with robust control where you can treat the nonlinearities as disturbances, or with gain scheduling to do different optimal controllers at different points. But the disadvantage here is that you rely on your knowledge of the dynamics. So if you have a bad model, you'll have a bad controller. So you could end up in a situation where just the model parameters are unknown, like inertias or damping coefficients, or you could end up with a situation like some complicated friction where the entire form of the model is unknown. The other thing here is that this synthesizes a linear controller for a nonlinear system. And so we may be leaving some performance on the table there when introducing a nonlinearity in the controller could potentially improve the performance. But the takeaway here is that if you improve the model, you can improve the controller. And so this is why we're going to start to care about using Koopman as the Koopman operator to model a robot. So when you have, in the case of the Mechademic robot, you have a robot on your desk and you want to make sure that this model that you have matches a real robot. You could, for example, just make reasonable assumptions about all the model parameters. You could assume you know the inertias from the CAD model, take damping coefficients or the gearbox from the datasheet, or you could further refine that by doing parametric system identification. So you could run the robot in a variety of poses and in a variety of paths and try and identify those parameters from data. But if you don't have a model for some parts of it, or if for some reason you don't want to use that model, maybe it's too slow to evaluate, you could learn a complete model non-parametrically. So fit the entire thing with a neural network or a Gaussian process, for example. But there are some limitations to all of these approaches, and it's that they all learn nonlinear models, and you'll need to linearize them if you want to use optimal control. And of course, you'll still end up with a linear controller for this nonlinear system. And another side note is also that some of these methods, like neural networks and GPs, are really great for learning functions, but really what we want to learn here is a differential equation. And so finding a machine learning method that's kind of tuned to learning differential equations is a very interesting topic. So I'll start now by finally introducing the Koopman operator here. So with the Koopman operator, a nonlinear system can be globally represented by an infinite dimensional linear system. So what we're doing here is we're trading finite dimensional nonlinear dynamics for infinite dimensional linear dynamics. So the kind of workflow that it might take for control here is that you lift the state space into an infinite dimensional space. You do this huge transformation, you take all kinds of nonlinear functions and you transform the state into an infinite dimensional state. You can then, the Koopman operator is responsible for basically acting like the state space model. It transitions the lifted states to the next lifted states. Finally, you can design a controller in the lifted space that's linear using optimal control tools, and then retract, so recover that control input from the lifted controller into a nonlinear controller. So what you end up doing here is designing an optimal linear controller in the lifted space, and then bringing that back down to the original space where it's a nonlinear controller. But I'm sure some of you are wondering what I'm talking about with this infinite dimensional system. You can't have that on a computer. You can't really work with that. So the key thing here is that we're going to use data-driven methods to approximate a finite dimensional Koopman operator. So instead of an infinite number of lifting functions, we'll maybe take 50 or 100 and see how close we can get. So this is a motivating example here for the Koopman operator. This is the best case we could possibly find. This is a case where there's an exact Koopman operator and it's finite dimensional. So if you look at equation 1 in red, there's this difference equation with a nonlinearity in it. But if you redefine the state in red over here to include the x squared term, you can write equation 3 that's a linear difference equation in terms of this lifted state, where you've basically appended this nonlinearity. So equation 3 and equation 1 are the same, but equation 3 is linear. And in this case, this 3 by 3 matrix with the lambda and mu is the Koopman operator. Now, in reality, we'll never be so lucky as to actually achieve this in a data-driven approach, but this is kind of the ideal of what we're going for, and it's motivation as to why we think this might work and might be valid. So this is, warning you now, this is the heaviest slide in the presentation, the most mathematical, but this describes the very underlying theory of what's happening with the Koopman operator. And then we'll go into how to approximate it with data-driven methods. So if you consider this nonlinear process, xk plus 1 equals f of xk in equation 4, what we can do is take these lifting functions, psi, and they're basically any function that takes the state and spits out a scalar is a lifting function. So sine, cosine, squared, anything that gives you a scalar and takes in the state is a lifting function. And what the Koopman operator itself does is it takes these lifting functions as input and returns functions as output. So what you see in equation 5 is the Koopman operator takes the lifting function as an input. And what it does is it composes it with f so that it gives you a new function at the output. And when you evaluate the new function and the old function, you see that one is a shifted version of the other. So theoretically, this Koopman operator is shifting functions around. So the takeaway here is that equation 6, where you have the Koopman operator advancing the lifting functions, is the same as equation 4. And of course, you want to approximate this in finite dimensions. So you take the Koopman operator becomes a matrix, and you take 10 or 20 or 30 lifting functions and use those. And you have a residual error there, of course. To actually, since we're doing control, or we want to do control, we care a lot about the inputs. So we have to modify the Koopman operator just a little bit to account for that. And so we care to predict the states in the future, but we don't care to predict the inputs. We know the inputs already. We don't want to propagate them forward. So that's why there's the 0 here in equation 8. The next trick that we do is we partition the lifting functions into 2 parts. The first part, theta, that only depends on the state, and the second part, upsilon, that can depend on the input. So we're splitting up our lifted states from our lifted inputs. And when we follow through there, we substitute that back in, the same equation 10 from the previous slide. You see that you recover the state space over here. You have theta at the next time step equals a times theta at this time step plus b times upsilon. So this is the lifted state space equation that we get by breaking apart the Koopman matrix. So this is what we can use, this A and B, to design a linear quadratic regulator, for example. So how do we get a Koopman model from data? Well, assuming we have a lot of snapshots, X and U, you can form these really big matrices that have all of the lifted snapshots. So in psi, you have the lifted state and input as each column from 0 to right before the end. Theta plus, however, is the same thing, but shifted by 1. So it's shifted in time by 1 time step. And you also cut out the inputs because you don't want to predict them. So then what you have is a least squares problem, a linear regression problem in terms of these 2 big matrices. You want to find the Koopman operator that best takes psi and shifts it into theta. So this can be solved with the Moore-Penrose pseudo-inverse. It's quite straightforward, quite simple. So data snapshots, big snapshot matrices, linear regression. So given that A and B that you find through linear regression that are both inside the U, you can do a state feedback controller in the lifted space. In 16, since theta contains all these nonlinear terms, this is actually a nonlinear controller over here. So this kind of reveals the potential to do nonlinear optimal control, given that you've picked your lifting functions correctly. On the left, you see a simple like toy example with the Van der Pol oscillator. So there, the orange controller is designed using a linearization of the Van der Pol oscillator, and the green one is a Koopman controller that's based on Hermite polynomials as lifting functions. So you can see the Koopman controller takes a qualitatively different path to 0 and also achieves a 20% lower LQR cost. So there's something here. If you do everything kind of correctly, you can do some kind of nonlinear optimal control. I'm going to summarize the Koopman workflow again, and then we'll get into some issues and some kind of open research problems with the Koopman operator and some of the work that Professor Forbes and I have done. So the first step is, of course, to choose your lifting functions. This can be done either through, well, the dream is to be able to pick them as domain specific, pick things that you think will enter into your model, but it's often not quite that simple. You could also choose standard basis functions, like I mentioned, Hermite polynomials, monomials, sine, cosine, Fourier basis. And also a very interesting one is using time delays, so augmenting the state with shifted versions of itself. So once you have this choice of lifting functions, you also have to collect data snapshots from either a simulation or from running your robot over a bunch of trials. You then can approximate the Koopman operator by applying all of your lifting functions to your data snapshots and solving a linear regression problem. You then have to test the predictive performance. You have to see how well or how poorly the approximated Koopman operator works. And then the problem is really that there's a manual loop here where you have to go back and refine your lifting functions to actually potentially achieve the best performance. You may not have used enough of them. You may have picked the wrong set, and so on. So there's this open problem for actually picking the lifting functions. So as I mentioned, choosing lifting functions is an open research problem. There's no right or wrong way to do it, or maybe there's plenty of wrong ways to do it. But the Koopman regression problem is actually very numerically challenging. Even though I said it's a simple least squares problem, it scales very badly with the number of lifting functions, and it can actually yield unstable or numerically problematic Koopman operators from situations that you would think are stable. The other thing is that not all, there's been some interesting work doing LQR and model predictive control with the Koopman operator, but there's still a lot of interesting linear control to apply here. But the thing I'm going to talk about is the numerical challenges, because personally, that's the first issue, that's the first roadblock I hit when trying to work with the Koopman operator. So when a lot of lifting functions are used, the least squares problem gives you an unstable Koopman operator, which is a problem because if you know your robot is asymptotically stable or it has stable dynamics, you don't want an unstable model for it. So regularization is one way to actually help avoid these issues. And what you're doing here is that you're adding to the cost function a penalty that says, I want the U that best fits the data, but don't make U too big. And by big in this case, we mean the Frobenius norm. But you can use multiple different norms for different effects. So you end up with this weighting parameter alpha that needs to be tuned either manually or through hyperparameter optimization and cross-validation. So using a matrix norm to regularize the problem works, it's fine, but it doesn't account for system properties. So we're really trying to learn a discrete time linear time invariant system here, and we're not actually considering any of the properties of that system here. We're just regularizing a matrix. The other thing is that it doesn't yield a stable system for all choices of A. You have to fiddle around with A or run the optimization many times to actually find an A that works. So I think we can do better than this. One solution here, which is some of our work in an upcoming paper, is to directly constrain the stability of the system. So you have the exact same optimization problem as before in 19, but in this case, you add a Lyapunov constraint to constrain the stability of the A matrix. You can even, in this case, specify a radius that you want, so you can add a little bit of padding when you're constraining the spectral radius of A. So if all the eigenvalues of A are less than 1, you have an asymptotically stable system. And if you constrain it a little bit further, that can help with the numerical issues. So we've tested this on data from the Fatigue Structural Testing Equipment Research Platform, the FASTER platform at the National Research Council of Canada. And in this case, the states are the beam deflection. There's a beam under test here, an aluminum beam, and the force on that beam as well. And the input is the actuator voltage. So we're trying to identify the dynamics of that beam. So in this case, the lifting functions are second order monomials. So it's the states plus all second order combinations of the states and input. And what you can see on the left is two different runs, one of them being constrained to have an asymptotic stability, just, rho bar of 1, so a boundary of 1, and the other having a bound of 0.99, so a little bit conservative. And this is the tracking, this is the prediction error for the validation set. So what you can see is the orange line is near 0, which is good for a while, and then it abruptly diverges. So there's this accumulated numerical error, and eventually it becomes effectively unstable because there's an eigenvalue too close to the unit circle. However, if you add a little bit of conservatism into that constraint, the blue line, which has the slightly tighter restriction on it, stays stable for the entire time. So if you look on the right, you can see the eigenvalues. There's one orange one really close to the unit circle, but if you adjust the constraint very slightly and you push back the eigenvalues very slightly, that's the difference between an unusable model and a usable model in this case. It's a very small difference, but the orange model is really not good for prediction. I wouldn't use it personally, but the blue one is much more well-behaved for a very small change. So that looks good for the asymptotic stability constraint. But I'm going to show you what I think is an even better approach here. Just a moment. There we go. So like I was talking about system properties before, you can actually think of the Koopman system as an LTI system, and that has a frequency response, it has a gain. So what if we regularize by penalizing the gain of the system and not by penalizing the size of its state space matrices? So that's what we do here. We use a system norm as a regularizer so that the system's gain is penalized instead of U. So we're saying we want a U that fits the data well, but the system can't have crazy high gain. And so that's what's expressed by the H infinity norm here of G. And so this is the state space system represented by A and B from the Koopman operator. And in this case, C and D are just 1 and 0, identity and 0. So the nice thing here is that this is actually stable for any alpha, because if a system has a finite H infinity gain, then you know that it is actually asymptotically stable. So I'll just go on a little bit of an aside here to solidify the H infinity norm for those of you who don't know. The simplest way to think of it is the peak of the Bode plot, the peak of the frequency response. This system over here, the magnitude plot, the H infinity norm is that peak there. So you can think of it as the worst case gain over all inputs. Or in the frequency domain, you can basically think of it as, in this case, the maximum singular value of the transfer matrix, but in a SISO system that would be simpler. But over all frequencies, what's the worst gain? So you can think, as we're doing the optimization problem, we're pushing down on this orange line to try and get a system with lower gain that still fits the data. So we tested this on an underactuated robot from the University of Michigan. And what this soft robot is doing is it's pointing a laser pointer at this platform here, at this board. And the states are the X and Y position of the laser pointer. The inputs are 3 pressure regulator voltages. And in this case, we had third order monomials as lifting functions with 1 time delay. So what that means is you take all the states and inputs, you shift them by one and add them in, and then you take all third order combinations of all of that. So that leads to 100 or 200 lifting functions. So it's quite large. So I'm jumping right to the end of the performance here, just so you can see what this looks like in time domain before we take a deeper dive into the properties of these different Koopman operators. So on the left, you see the X and Y tracking performance, the prediction performance, and the error is pretty close to zero for all of them. Qualitatively, these models are all fine. The orange being extended DMD, the linear regression. Blue being the asymptotic stability constraint, which has some bad spikes of error later on. And then there's also in green, the H-infinity regularizer. So this is just one time, this is one validation set. But if you look on the right, it's a summary of 4 different validation sets. So this black bar tells us the standard deviation and the mean over the 4 sets. And the error of each set is actually shown individually. And so what's interesting about this is that extended DMD and the constrained system do really, really well for some sets and do really badly for other sets. There's a huge spread. They're not very consistent. Whereas if you look at the H-infinity regularizer and the weighted one, which we'll get to later, you can see that they perform a little bit worse on average, but they're very consistent over the 4 different validation sets. So that's telling us that maybe there's an advantage to using the H-infinity regularizer that's not just mean error. We don't just care about the mean error here. So I said part of the nice thing about a Koopman model is that it's interpretable in a way that maybe a neural network would be not interpretable. So what we're doing here on the left is looking at the eigenvalues of the A matrix, so the Koopman A matrix. Right away, what you see in the orange dots over here, the orange eigenvalues, is that it's unstable, and by a good margin too. So we've learned an unstable Koopman operator with the linear regression for a stable system. And on top of that, just because it didn't diverge in any of the validation sets doesn't mean we want an unstable model. So I would discount the linear model right away because of the instability. But if you zoom in, you can see that the asymptotic stability constraint and the H-infinity regularizer are both still stable. So that's nice. They're both doing what they should be doing, giving us a stable system with similar performance. But that's not even the whole story, really. What you can also look at, another way to view some of this information, is through the singular values of A and B. So we're getting the singular values will tell us roughly how big are these matrices, how big are the entries, what scale are they at. And so if you look at this is a logarithmic scale, by the way. So if you look at the orange line for the linear regression method, you have singular values in the thousands and trailing down. And that's the A matrix. And in the B matrix, you also have singular values in the tens of thousands. So these are matrices with big numbers in them. However, when you constrain the asymptotic stability in the blue line, you see that as expected, the singular values are all under 1. So that's nice. We've made the A matrix smaller, but if you look at the B matrix, we've made it worse. We've actually made the singular values even bigger. So by constraining the A matrix, we've shifted everything into the B matrix, which arguably is even worse conditioning numerically. Because we have now a matrix, an A matrix with like everything under 1 in it, and a B matrix with stuff in the tens of thousands. However, if you look at the H-infinity regularizer, which considers the system as a whole, not just the different parts, you see that both the green line on both of them are under, in this case, under 1 and under 10. So it's much more reasonable numerical conditioning there. Another way to look at this is to look at the frequency response of the systems. So you see that the gain is very high for the linear system, and it's got this weird peak as well at a random frequency. Constraining the asymptotic stability doesn't even help with the gain. The gain is still very high. But if you use the H-infinity regularizer to push down on this gain, you see that it's much lower, and again gives very similar, if not better, performance. The cool thing, if you know anything about H-infinity control, is you can use some of the tricks from control in regularization. So over here, we can actually weight the norm. So in this blue dashed line that uses the right axis is a weighting function. So what we're doing over here is we're saying, I want to penalize, oops, I shouldn't have clicked. I want to penalize gain at high frequencies because I don't trust the data at high frequencies. And I don't want to penalize low frequencies so much because I do trust the data more there. So you're kind of expressing in what frequency band you trust the data more or less. And so then you can see the impact on the frequency response is that it has a higher gain at lower frequencies and a lower gain at these high frequencies. And so if we flip back to the original plot here, the difference isn't that drastic in this scenario, but what we're actually doing is trading a little bit of standard deviation for a slightly better mean. In this case, they're quite similar, but the ability to actually weight the system using a system norm and not just a matrix norm, and even be able to adjust where you trust the data and where you trust the lifting functions is a really cool contribution, I find. So for those of you who are a bit more code oriented, this is your time. Through all of this, we came across a lot of problems actually implementing some of this stuff. The biggest thing is that Koopman has a lot of bookkeeping, and it has a lot of bookkeeping that is not super well supported by machine learning libraries that are focused on learning functions, but we want to learn time series. So one of the things is composing lifting functions. You need to track the ordering to keep all the inputs at the bottom. You need to make sure that you know where all the inputs are so that you can undo them. So PyCoop, which is our library, our open source Koopman library, lets you basically make a list of lifting functions and it'll compose them for you. And it introduces scikit-learn compatibility to let you cross-validate over different lifting functions and over different regression parameters. So what this looks like, the simplest case is just that you create a Koopman pipeline object. This all follows the scikit-learn conventions. Then you have this list of lifting functions here. In this case, there's a polynomial lifting function of order 2. And then you can specify your regressor over here. Once you've done that, you can fit the pipeline, giving it the number of inputs, same as scikit-learn. And then you can use that to predict. You can use the fit model to predict on new data. So what you're able to do here is just add to this list of lifting functions. So I want to delay, and then I want to scale, and then I want to do a polynomial, and it will track and invert and do everything for you for these lifting functions, which when you try and code Koopman yourself, the first time is really not trivial. It's very easy to get burned by. So this also provides an interface for other people to write their own lifting functions and have them work with the existing ones as well. There's a common interface there. One cool thing that falls out of this scikit-learn compatibility is you can cross-validate different lifting functions. In this case, you see the polynomial is highlighted here, and I'm gridding the different orders, first order, second order, third order, and gridding the regression parameter. And even here, you can cross-validate over different types of lifting functions as well. So this has made my research a lot easier, and I'm hoping that some people will maybe help build on this, and it could be useful for them. Of course, I have to thank the sponsors of this research on behalf of Professor Forbes and I, Macademic, MyTax, which is partnered with Macademic, and NSERC as well. So all of this work is going to be submitted to a journal soon. You can see it on arXiv if you want in these 2 preprints at the bottom, and also take a look at our PyCoop library if you're interested in trying some Koopman stuff yourself. So thank you everyone for your attention, and I welcome any questions that you have about this.
I have a question, Stephen. Thank you very much for a very lucid presentation and fascinating work. detail, perhaps, is the sampling rate. It seemed that the discrete time increment was taken as absolute of course, for the presentation, and that simplified things. But what happens as you vary the sampling rate?
I would say that that's generally system dependent. I've actually noticed some differences when, just a moment, when subsampling and playing with the sampling rate. And I've seen other research done by other researchers that play with the sampling rate as a hyperparameter. So I would say, first of all, that depending on the system, you have to pick your sampling rate in the usual way. Be sure that it's fast enough to capture the dynamics that you care about. I don't have an answer for you that's general, saying that it has this effect everywhere, but depending on the system, it absolutely has an impact, and you need to choose it carefully. And there could be reasons that you would want to go with a lower sampling rate or a higher sampling rate, but I would say it's very system dependent. And you can see, for example, in some of the soft robot research, when the data was resampled, if it was resampled at without an anti-aliasing filter, for example, there were lots of problems in the fit, and it was hard to get a good Koopman fit. So it's something you have to be aware of, and it's a design variable, as always.
Thank you.
Thanks for your question.
Stephen, there's also a question in the chat from Michelle. He says, how easy is it to get started with the PyCoop library? Any fun or plug play applications for a beginner in Python?
It's if you already are familiar with the scikit-learn tools, which are kind of the standard tools for this type of work, it's plug and play with all of those. I'd like to think you'll have more trouble with Koopman itself than with the library. I think that there's been a lot of effort put in to make sure that it's user-friendly. But I think it would be very cool maybe in the future that I might make a Jupyter notebook that people can try out online, and without having to install it and everything on their computer, give them the opportunity to play with Koopman in a safe way.
Great. Thank you for the talk today. Does anyone else have any more questions?
So I have a question. Oh, go ahead.
Go ahead. Sorry.
Thanks. So I've been meaning to look into this the Koopman operator for a while. It's very interesting. But a question I have is, it looks like essentially what you're doing is kind of like kernelized linear regression with time series. And I know there's reasons why people sometimes use neural nets over that, for example, overfitting. So I guess one question is, have you experienced any of that? And also, how would your work scale if you wanted to work on higher dimensional systems? Like if you had a humanoid robot, I would expect like the lifting function, you'd need like combinatorially many lifting functions.
So a few things there. First of all, I think you had a good insight there with the lifting functions. You can actually represent the lifting functions as a kernel. Instead of explicitly saying, I want 100 polynomials, you can represent that as a polynomial kernel, and then do something called kernel dynamic mode decomposition. The problem with that is it's very difficult to then go back and, like when you're doing control live, you need the lifting functions. The kernel won't be enough to actually do the control. And it becomes very hard to separate out the control input from the state with kernel methods. So there's definitely some cool stuff with the kernel methods, but I find it challenging for control. As for the neural network stuff, maybe a nice aside is that you can actually represent your lifting functions as a neural network, because in some ways, just picking polynomials is not always, it's not the most general set of basis functions. You could just think of it parameterized by a neural network and do kind of a two-step thing, optimize your neural network, optimize your lifting functions back and forth. Now in terms of scaling, that's where it gets bad. Like I had to buy more RAM for some of this. It's pretty rough. for the scaling to large systems, that's where kernel methods can help, but that's still kind of an open research thing to deal with kernel methods plus control. There are methods to do dimensionality reduction. So to learn a Koopman model and then throw away unneeded observables, unneeded lifting functions, so that you kind of control that complexity there. But in terms of, if you start with a lot of states and you have a lot of lifting functions, you're definitely stuck with a lot of lifted states. So, oh, but actually, wait, I did research on this. You can also project the whole problem onto a subspace and solve it on that subspace, which basically saves you a lot of trouble. So it would lift everything and then do the SVD, and you can actually project this whole problem down using dynamic mode decomposition. And that will make the regression problem smaller, but you still have to handle that. You still have to handle a lot of data at the input and output of that. So if you're interested in the dynamic mode decomposition stuff, it's in the preprint.
Awesome, thank you.
Thanks.
If I may, I'd like to inject a question here. Thank you. First, thank you for the very interesting talk here. My question, first question is related to the existence of a Koopman operator for general nonlinear systems. At the start, we start with a definition directly on the Koopman operators, but we did not seem to study or discuss the existence of these Koopman operators. For do we have conditions under which one can check the existence, or it's not a question at all?
So yes, actually, I believe, unless I'm wrong on a detail here, I believe theoretically the infinite dimensional Koopman operator always exists.
Mm-hmm.
Now, the existence of a finite dimensional Koopman operator is not a given.
Mm-hmm.
There are some conditions on whether you can actually even hope to get a finite dimensional Koopman operator. For example, if you have multiple equilibrium points and you choose your state to be part of your lifted state, that right away says you can't find a finite dimensional Koopman operator that's exact. You could still maybe hope to approximate it. I believe there's actually a partial differential equation related to solving this, but to actually finding the Koopman operator another way, but that's quite challenging to solve the PDE. And if you're interested in that, I would check out Igor Mezic's work on that, because he talks a lot about the more fundamental stuff about whether the finite dimensional Koopman operator can exist and stuff like that.
Thank you. I think I have another question related to your motivating example where you have this 2 states and extended into 3 states.
Sure.
I was wondering, just for that particular example, if one implemented this scheme here, so the first state in the extended state, it has a relation with the 3rd state. So I was wondering, when we apply this technique, do we need to check the relation between the 1st state and the 3rd state? Like, or it's not it's treated as independent state?
So that's an interesting question, and that's actually the fun thing is that there's 2 ways to propagate the Koopman operator, and there's 2 ways to predict using the Koopman operator. So one way is to start with your initial condition, which has to be valid. So, you know, the x1, the x0 and the x0 squared have to be consistent. And then you keep multiplying by the Koopman operator to advance the state. So you go basically Koopman operator, Koopman operator, Koopman operator, and you end up with propagating the state. So that's not guaranteed to keep the relationship between the 1st and 3rd state.
Mm-hmm.
However, there's another way to do it where you can multiply by the Koopman operator, extract out the first 2 states, and then relift, so that between every multiplication of the Koopman operator, you're guaranteeing that the relationship between the first 2 states and the 3rd state holds. And so those are 2 different kind of metrics for different applications. The latter is more useful for control because that's how it would happen in a real system. You would measure sensor inputs and lift them as you go. So you would lift every time. But it's basically two different ways and two different kind of metrics that you might care about.
Oh, thank you very much.
Thanks.
Actually, my question was a follow-up to Shuang's, because I tried to work on, so in the model that you have right here, if we add U to any of the equations, then we get a very nasty relationship, just like, never ending, and also having equations like multiplies X squared, like U cubed, and so on. So I was wondering, like, when you are talking about the B metrics, is it the lifted input you are talking about? And we have much more constraints in the input space now. If my U1, U2 is just like, X cubed, U to the power 5 or so. Like, we don't have access to the conventional control inputs when we are discussing that.
Yeah, so that's actually a big problem, and one of the limitations of Koopman operator theory right now is that all the people who have successfully done control have not lifted the control input. They leave the control input unlifted, which is, it simplifies actually retracting the control to get your control input, but it leaves a lot of ability to express the system on the table. So you're trading off there. One interesting piece of work done by, I think, Daniel Bruder and other collaborators of his is to do a bilinear lifting. So what he says is any control affine system can be described by a bilinear Koopman operator, where you take your lifted X, and then you don't lift the control, but you do products of the lifted state with the control. And he showed that that's a very convenient form to work with. And also it can express a lot of the systems that we care about in robotics and control. So there's some interesting work being done in that way of picking lifting functions in a way that is amenable to control while also being able to represent more interesting systems.
Thanks.
Thanks.
If I may ask another question,
Mm-hmm.
it's a follow-on to the follow-on, really, that I know James is very interested in partially observed systems and recursive estimation theory for nonlinear systems. Has there been any work on partial observations in this setting? Because that would seem to pose some very tricky issues as to where the estimates end up if you need to do projections.
Yeah, it does pose some problems. I believe there has been some work done on it. What comes to mind right now is observers using the Koopman model. Mm-hmm. However, if you actually try and do a Kalman filter, the issue is, sure, you can propagate your states through the observables, but you also have to propagate your covariance matrices through the observables. And that becomes tricky. You have to get around that, probably with like sigma points. So there's definitely some work being done on it, but I think it's more challenging than the control problem. And I haven't really dipped my toes into that yet.
Thanks.
Thank you.
I could follow on to Stephen on that, Peter. So the short answer is actually yes. With a collaborator of mine, Tim Barfoot, we've actually been looking at that exact problem. And the way we actually approach it is we assume we actually have a training set where we actually have quote unquote ground truth data. We have all states, all measurements, we have everything. And using not this exact pipeline, but a similar pipeline where we have lifted states, we can actually form a very large, basically least squares problem, and actually, quote unquote, to use the machine learning lingo, learn the A, B, C, and the Q and the R. We actually learn the covariances as well. Yeah. Like we learn the whole thing. And then once we have, quote unquote, learned all those things through just some fancy least squares, we then can take a partially observed system and then estimate the lifted states. And from the lifted states, we can extract the true states. And we've actually had one paper on that. It actually worked out pretty well. And what I find amazing about that is that we have effectively been able to, and not just me and my collaborator, like some other people have been working on this too. We've effectively turned this nonlinear state estimation problem into a linear state estimation problem where we can leverage Kalman filters, smoothers, name a linear filter you want, you can leverage it. So that's, I think, pretty exciting.
Wow. Thank you.
If I may inject, I'm wondering, when the learning that you mentioned that A, B, C, and QR simultaneously learned, I was assuming that the QR are the design. Is this under the LQR problem where the QR is the cost matrix? And I was wondering, is that part of the design or how that is learned?
They're actually the covariance matrices of the noise. It's a bit of a notation conflict.
I see. Sorry.
Yeah.
I see. Thank you. Thank you. If there's time, I'd like to add another question. Very interesting talk. So I was wondering, with the H-infinity norm regularization, I was wondering what the complexities and the issues there.
You got me.
I was curious how that's done.
Yeah, it's a bilinear matrix inequality. So the way we do this is we reformulated the Koopman problem as a linear matrix inequality. But the problem with, so right over here, you've seen 39, 40, 41, 42. That's just the regular, that's just the standard Koopman problem as a linear matrix inequality problem. The issue is when we add on the H-infinity norm, both A and P are unknown here, which means that this becomes a bilinear problem. So it's non-convex, and the way we solve this is by solving half of it with A fixed, and then resolving it with P fixed, and going back and forth and iterating. But it can take quite a long time for large systems with many lifting functions. So there's nothing for free here. But I would argue that it still takes less time than running your hyperparameter optimization for days.
Thank you.
Thanks.
All right, if there are no more questions, then we can wrap up here. Thanks for the excellent discussion and questions from everyone. And thank you, Stephen, for this excellent presentation. I think it sounded like it sparked a lot of interest in the control group here.
Thanks, and of course, thanks for organizing. It was really great to be able to talk with you all.
Great, thank you all for coming.
Thank you
And
very much.
see you next time.